So good afternoon, everyone. A very warm welcome to this webinar. It's my pleasure to introduce Antonis Giannopoulos and Nathan Mano, who are here today to talk to us about the work that they've been doing with gprMax and MPI. Please take it away, Antonis.
Thank you very much, Claire. Good afternoon, everybody. Thank you for joining. My name is Antonis Giannopoulos. I'm a professor of applied geophysics and computational electrodynamics in the University of Edinburgh and been working on GPR and electromagnetic modeling for quite a long time. So what we're going to do today is we'll share a presentation with Nathan. I will talk a little bit about gprMax, the easy things, the history, what is GPR as well, because I suspect most of you don't really use GPR, and why we're here and what this code is doing. And then Nathan will talk about the interesting things about the MPI. So without wasting more time, I will start the presentation. Yeah, here you go. So basically, gprMax is a full wave numerical modeling code that is based on the finite difference time domain method, a very well-known method for solving Maxwell's equations directly in time domain. And initially was developed very long time ago for some of us to model the complex responses we get for ground penetrating radar systems. The name gprMax comes from GPR, which is ground penetrating radar, and Max from Maxwell. And given that gprMax started quite some time ago, for many of us, only 6 letters was allowed to an executable file in some of the platforms that were working at the time. So here's gprMax with 6 letters. The links below is where you can get it from our website or GitHub repo, and also where our documentation relies. But it's very easy to find it if you Google gprMax. It will come. Very, very easy. Now, what is GPR? The first kind of part. Basically, GPR is a term we use to describe both equipment and a geophysical method, and is used in many, many ways to assess infrastructure, to find archaeology, to insecurity, in many planetary radars at the moment, for example. It has a range of applications when we send electromagnetic signals into an opaque object, normally the Earth, but doesn't have to be the Earth. It can be a concrete structure, for example, or something else. And these electromagnetic signals reflect from discontinuities on the electrical properties of the various materials. And these reflections come up, we'll record them, and then we'll try to analyze them. That is the difficult part, really, because trying to actually analyze what these responses mean is the part that we're actually working all these years, especially with gprMax. And here in the pictures, we can see various GPRs from various manufacturers on how they can be pushed and pulled along, and some of the data, how they look like. Now, the easiest way to understand GPR is that if you have a very simple simulation, you have a source and a receiver very close spaced, almost at the same spot, and then you actually let the source and send an electromagnetic pulse. The pulse will hit the object. The object will create another response, which will reach the surface. It will be recorded. And as you can see now in the video, this procedure is repeated. Is moving along a survey line. For ground penetrating radar, our targets are buried. They don't move, so we'll move the radar instead. Well, normal atmospheric radars usually are stationary, and the targets usually move around them. So this is basically the process of detection of a GPR system. What you get is that if you have a source and receiver where the star is, at time 0 you get nothing. Then after a while you get a very strong response, which is the direct wave from transmitter to receiver, normally the very early part of the signal. And then you go on waiting and waiting because nothing is happening, although inside the opaque object the waves propagate, the waves interact with the target, they reflect. Eventually something will arrive after some time, and this is what you get. It's a single trace. We'll call it wiggle trace or an A scan in GPR, and this will be recorded normally on a grayscale or a color scale, as you see on the right-hand side. And what we do, we take this trace, color-coded, we'll collect all of them in the different positions, and we'll get some patterns. And here you see a simple hyperbolic pattern that is common on targets that is long and thin, like your cables or your utilities and all these things. And obviously the constant response on the top, which is basically a direct signal from transmitter to receiver. So that's basically what GPR is doing. Life is obviously not so good. When you have real structures, here is a building in the University of Edinburgh, the William Rankin building, and we scan two scan lines across the concrete slab, and you can see the responses of the reinforcement inside this scan. So you can see various hyperbolic events, and this is basically mostly responses from reinforcement or from metal tenons that are inside this concrete slab. So that can help us locate things if we have lost them or if you need them for any reason. Life is a lot more harder. Here is an example of simulation again from an anti-personnel landmine. It's a thing that will work, and GPR is used with it. You see the sources obviously is not on the surface because it's dangerous, and then you see the interaction of waves with complex rough surfaces, complex material. Small little complex targets are a lot more complicated than actually what would be a single simplistic model. And you see that interpreting this kind of responses that come up now, very faint and very complicated, is really hard. That's why we need to model them and understand these responses. How we do it, we solve Maxwell's equations, which we'll see here. And how do we do that? We use a finite difference time domain technique, which will, based on approximating the electromagnetic fields in various components in a rectangular cuboid, most of the time, cell, we would call Yee cell, from the person that is actually invented this technique years ago in 1966. And what you notice there is that all electric components are not located at the same spot, and both electric and magnetic components are spaced apart. Equally, they're spaced apart in time as well. And that creates a leapfrog numerical solution of this angular differentials equations, which is very well established of how it happens. It's a conditional stable, and in essence, a wave propagator. The way it mimics Maxwell's equations is very simple to see with this simple animation here. For example, if we want to calculate the line integral on the left-hand side, that will relate to the time derivative on the right-hand side, which is represented by this y component. So this simple looping in a very simplistic algebraic form mimics Maxwell's equations, and it's obviously if the delta x, delta y, delta z are very small, this mimicking, if you like, becomes quite accurate and quite nice, and you can solve complicated problems by assigning electromagnetic properties in every single component, and this way you're building objects that you want to simulate and get the electromagnetic response. Now, short history of gprMax. gprMax started in 1997, and it was written in C by myself. And for many, many years, it was a free code that it was given to people to use for 2D and 3D modeling, but it wasn't properly open source. That means that the source code was available if you requested it, but not openly given to anybody. Primarily, that was coming out of embarrassment for myself because I didn't want people to see how I did it, just to be embarrassed by people saying, oh, it's not really very nice. That's a very stupid thing if you want to involve with open source. You just put things forward is good for other people to use. Anyway, in 2015, some time ago, we have been working on various research aspects of numerical modeling with my students. At some point, we got some funding and we decided, let's do that properly. We rewrote the code. We used Python and Cython for the fast part, so C in essence, and all sorts of open, nice tools like HDFI for storing information, ParaView for visualization, and VTK obviously as that. We use read the docs to put all our documentation and all these things. And we created the first version. We call it Bowmore. We call it after whiskeys. Every version has a whiskey. And that was around 2016 when it came out. 15, 16, it was the main development. We published that in a paper, and it's now gprMax from then is what you call free, as in freedom, under the GPL version 3, and properly open source, so people can contribute to it without really knowing, being in a way overshadowed by someone who runs the code only for their own benefit. Then after that, we had a small collaboration with Google some time ago, and we developed in 2017 a GPU solver, which so that it gave us huge amounts of improvements in terms of speed. And as we see from a graph here, I mean, this is a very old graph with the old GPUs for today's standards. But the speed up in when it is compared with the CPU is really phenomenal, and it went really very well, and allow us to do really bigger, complicated models a lot faster than we used to do before. We do have quite a good spread of people that actually using the code. Actually, someone put a dot in Antarctica. I don't think that is anyone using it in Antarctica, but there is a number of people that are using it for various kind of simulations, primarily on geophysical work and GPR, but not only. Now, one thing we can see if you go to our website, you can see, for example, the papers are using gprMax, the people who cite our works, only 2 or 3 of our papers that actually relate to the code themselves. And this excludes self-citations. You see here that this actually the impact is increasing from over 20 years. And what is interesting to note this is basically that when gprMax was free as free beer, it had a good impact, if you like, but it was a lot less. When it became free as in freedom, the impact and the people are using it, the people that contribute to it is a lot more, and becomes a much more valuable tool for the community that tries to use electromagnetic modeling. That's basic capabilities. I'm not going to go into details of that because we need to have time to discuss the more interesting things with MPI. We have our own perfectly matched layer boundaries. We have very good boundaries that can be customized and offer a very good absorption at the edges of the domain. So when you simulate, as we do, mostly open boundary problems, that means that there is no termination of the wave at the end of the model. We're supposed to model an open space. Then these PMLs, these perfectly matched layers, are our own formulation, and can be customized, and they have very good performance with very small errors, even when the sources or the scatterers are close to them. So we're very proud about this kind of work. Also, we have developed our own recursive convolution of adding complex frequency-dependent material in our solver. The solver is purely time domain, so obviously when you have something purely in a time domain, it's not as easy to describe properties that are actually frequency-dependent, and therefore we do have developed a technique that allows us to do that, and actually we can model debye, Drude, Lorentz media, and also multiples of this kind of media. Multiple debye material can be used to simulate pretty much any variation of frequency domain, permittivity, and conductivity, which is the key electromagnetic parameters that you're interested in. As I say, sometimes, I mean, if you want, you can get gprMax to model graphene or any complex things that you like. We do diagonal anisotropic materials, what I call the cheap anisotropy. This doesn't really change the fundamentals of the code. They can be done quite easily, and therefore we offer that so you can have anisotropy if you are diagonal anisotropy, which is the key and simpler case of anisotropic materials if you want. We do automatic dielectric smoothing at the cells, at the cell boundaries. This is a classic thing in FTDD, as you're having these small cubes of material properties, if you like, and where the electromagnetic fields are, you need to take care of the interface in between 2 different regions, and we do that automatically for the user, or the user can switch it off as well if it doesn't really want it and wants specific properties of specific cells, but this is done automatically. It's called sometimes a generalized Yi approach, if you like. And also we have a lot of functionality to model ground penetrating radar, or if you like, geophysical electromagnetic propagation. It doesn't have to be radar. And therefore we have developed techniques to do more realistic stuff in terms of soil modeling. For example, we use fractals, which is not a straightforward thing to do. You use Beklisking model for soils, which you describe the properties of soils with frequency-dependent materials, and you can just describe your soil with your clay content, the sand content, a little bit of water fraction you have, and then it will generate statistically correlated type of distributions of soil, which is really very helpful. We want to simulate something which is more realistic than a homogeneous block of something that you call it sand or concrete or anything. So that allows you to do a lot more faithful simulations. Also, stochastic distribution of material properties includes the stochastic distribution of creation of rough surfaces. So you can have rough surface interfaces, you can have water puddles if you like, We can have even grass blades and things like that that come into play. So you can actually simulate very faithfully environments like this. This work was sponsored years ago from by TSTL, when we have a couple of PhD students working on trying to create models, accurate models of anti-personnel landmines. These landmines are very small targets, are really hard to actually discriminate by other targets because it's primarily plastic, and therefore they have very small minimal metal content. Therefore, metal detectors do get a small response, but not a proper big response. So radars are used here to try to detect them and discriminate them. Also, some people have tried gprMax with in bioelectromagnetics, and there are some papers that people trying that instead of other bigger commercial codes. Here is some models that were created by using the Austin Man or another model mesh from ITIS. So we can get these things, we can read them into the gprMax and try to mesh them automatically, and therefore you can actually use that code to actually do other things than GPR modeling. In a way, the code is quite generic in that sense, so it allows you to do a lot more things. And this is the direction that we want to go as well, make the tool a lot more useful to other people who want to do computational electrodynamics and not necessarily only around GPR. Some simple examples. You can easily create simple models with a simple input file that we create. This is a range of commands that we have that allows you to create your model. You give a title, the size of your model, discretization, the length of your simulation if you like. Then you have objects and waveforms and excitations and sources and outputs that you can easily simulate here. Simulate a simple linear dipole. This is a way we introduce to most users to use our code with a simple input file. But in our development branch that we have the new gprMax is coming out, we're offering the capability of using an API and do that more programmably, which is a lot better, and you can do a lot more complicated things a lot easier. So here, for example, you can run this model and get what we call the S11 parameter of a simple linear dipole, which tells you the resonance frequency. That's nothing really crazy or important about that. If you're doing antennas, you see this result even in books. Also you can do, we have tested our algorithm with other techniques. Here is a simple model of a linear dipole over the electric half space, and where the stars are, for example, are the output points of what the fields can do inside this material half space. This is not a straightforward problem to do analytically. Actually, it's quite hard to do analytically. There are numerical techniques that solve it, and with this problem, we use it to compare our code with other codes. Here, you see the results of the current of this antenna and the points of the electric fields in various locations with different depths, as compared with our code, which is FTDD, with finite integration, which is again similar to FTDD, but is a commercial code, this is the Microwave Studio, and with the time domain integral equation technique by another group. So you see the agreement is quite good, especially the two, the commercial code and gprMax agree really very well. So we're confident that our solution is okay, because we actually compare it a lot with commercial tools as well when we can. We do a lot more complicated stuff. We model GPR radar transducers, which are quite complex. So here is, for example, antennas, real GPR antennas, which we open and we study what is inside. What you see here is the transmitter and the receiver of two GPR transducers and the bow tie antennas that they employ. Both of them are different manufacturers, so they're a little bit different. Our model is very accurate of them. You see that they're represented really well with any detail that we need to. And therefore, once we're trying and compare our results with real data, now we actually can see that this works really well. But what that helps us to do, for example, is to actually simulate the electromagnetic propagation of complex pulses in these sensors and try actually from other people who use the code to design better antennas for this purpose and make them radiate cleaner signals, better signals, and also understand how the radiation patterns of these antennas evolve, which otherwise will be very difficult because you cannot really, you can measure them in air, but you cannot measure them when they're above the half space because you don't have sensors like that embedded in the half space. So this, the SO patterns of these antennas can only be measured or computed, if you like. And you see that when we compare our results again with the commercial model of these same antennas and our model, and with the real data, we get very good correspondence and faithfulness in our models, which are really very important. Now, we do this in terms of what we want to call more advanced applications, primarily on GPR, but other people use it for other areas as well. And here is a more recent work when we model this red little antenna up there, the transducer, with great detail. The correspondence between real and synthetic data is very good. And what we've done with it, we then created a machine learning framework where for specific problems of reinforcement embedded in concrete slabs, we trained a neural network to actually give us some predictions in terms of what the responses might have been for specific targets, and also to be able to give us some predictions automatically from the received data about the background bulk properties of the material. And this is all part of a machine learning framework, which work really, really very well. I'm not going to spend time to analyze the details of these two papers because it will take too much time. But what we managed to do by using this machine learning framework trained with a lot surrogate data created by gprMax using a very good antenna model allow us to automatically process very complex data, which otherwise we wouldn't be able to do that. Again, we work a lot in landmines with trying to create more sophisticated models to give more understanding of how complex is this interactions of these little targets in very complex environments with radars, and therefore try to give the ability to people to develop better processing algorithms if you have a good electromagnetic model of what is supposedly happening. What is the worst situation here is that people using very simplistic models which don't represent reality and then wonder why the processing algorithms fail. So when you have tools like this, it allows you to understand more what's happening and therefore develop better tools. Another area that we're actually working a lot is on planetary radars. You all have heard about Perseverance and the rover, the NASA rover that runs on Mars. This has a ground penetrating radar on it. It's called RingFax. And a lot of the modeling, the group that uses RingFax and some of our students as well, will work with gprMax to try and understand through modeling the complex responses they receive from this radar system. Equally, we do work ourselves and as well other people with the extensive data from the Chang'e Chinese missions to the moon, the U2 rover, where it has another radar system on it. And as you understand, radars, pretty much this type of radars for planetary exploration are, in a way, I will say, the best tool you can use because you can send it there, get data without requiring either to hit something, as we do with seismology, or and have someone there to do more active geophysical techniques. So you can create some data from the inside of this kind of remote environments and try to analyze them ground penetrating radar. So these kind of sensors are in planetary geophysics, if you like, quite upcoming, and that's an RS application that we're working on and other people can work in. So what is the future and the state of the gprMax at the moment? We do participate in the Google Summer of Code. We've been for quite a few years, where we are very lucky that Google gives us some interns in the summer and work in aspects of the code. And it's very nice to be selected out of 40, 50 science and medicine applications every year. Having the code next to Python, for example, is embarrassing to say the least. But it's really helpful for an open source code like that. It's basically led by a few academics, and it's very hard to keep up and be able to work on it all the time. We actually have a new beta version out. Sadly, it's been out for quite some time, but this version has the ability to do subgridding, the ability to do very interesting things like more solvers like OpenCL support. Now we have a metal for Apple Mac as well, the CUDA solver, obviously. We have various toolboxes that are coming out to help people do more models. But the biggest thing that we have is that we managed to get funding to, I have a project with EPCC, what Nathan is going to talk in a minute, about being able to create an MPI domain decomposition solver for gprMax. That brings down one of the biggest limitations that you have with these models, that the size has to fit in your computer or in your GPU. And if you cannot, then that's it. We can do task farming. We used to do task farming for running various models many times, but that's not really solving your problem when you have very, very big models that you want to run. And that is basically what was everything about this project on the large scale open source computational electrodynamics and the MPI domain decomposition solver that we got. So with this, I will pass on to Nathan, and I can take questions later on when Nathan finishes as well, and we'll discuss any questions you might have. Okay, thank you very much for listening.
Thanks, Antonis. If I shall swap over the screen sharing so I can control the. Yeah, thanks, Antonis. So yeah, as mentioned, I'm going to try and give a bit of an overview of the ECSU project that we've been involved with here on gprMax. It was kind of a 2-year project that kind of finished in the summer. So I'll try and cover as much as I can in the next 20 minutes or so. That's what we did. So as Antonis mentioned, the main aim was to add an MPI domain decomposition to gprMax. So this was to the CPU solver. And yet the main target for this, whilst slightly performance, was mainly capability. So the maximum model we could run on, giving ARCHER2 as an example, with a 256 GB of memory on a node, was 1.6 meters cubed at 1 millimeter resolution. So that's about 4 billion cells, which is already quite a lot. But if you want to add more complex geometry, so as I mentioned, the stochastic kind of fractal geometry that uses more memory. If you want to take snapshots of your electric or magnetic fields, that can increase your memory usage. So we want to get over this hard limit. The existing gprMax solvers, so the CPU solver was parallelized with OpenMP, the GPU CUDA one, OpenCL, the Apple Metal. All of these solvers are limited to a single node or a single device. So to run large simulations, we need more memory, which we can do by giving our node more memory. But particularly in the case of, there's a limit to this, and particularly in the case of the CPU solver, there's a limit to how much OpenMP can scale within a node. So we can give it more memory, but we won't necessarily have the performance to back that up and do the computation in a reasonable time. So yeah, adding MPI domain decomposition, it means we can scale beyond a single node and hopefully add a bit of performance as well. So from a user point of view, the aim was to make the change as minimal as possible. So no need to change the model definition, simply add this new MPI flag to the run, and then followed by the numbers to specify how you want to break up your domain. So here we've got the gray box with kind of our main domain, and then we're going to decompose by 2 in the X, Y, and Z dimension. And so that gives users a lot of flexibility to decide the decomposition they want to use. And as we'll get onto, can have performance implications as well. That is the idea. So let's look at how we actually did this. We can start with the kind of a simplified version of the main solver that gprMax uses. So for each iteration, we're going to be storing some outputs. So that's going to be receivers, so they're point sources in a grid. Store the values of the electric and magnetic fields. Store snapshots, so that's views of the electric and magnetic field, but kind of on a larger scale across a wider range of the grid. We're going to update our magnetic and our electric fields using as our Maxwell equations, solving those. So to do the kind of halo exchange, to do the decomposition, because each rank has a subset of the grid, we need to add in some halo exchanges. So the earlier saw the Yi cell that had kind of +1, -1, etc. on it to do the points on the grid in order to do an update. So we've got kind of what depth of 1 halos on all of our local grids. So after we've done the update, we need to do a halo exchange. This is just direct point-to-point communication done with asynchronous MPI calls. And then we also need to do slight updates to the snapshots because these also require a halo exchange because they do some averaging, but their resolution might be lower than the main grid, so they're going over MPI boundaries. So they do require their own halo exchange. But the important thing here is there's no global communication. It's all this neighbor communication. There's actually also no I/O. snapshots are stored in memory, which has its own pros and cons, but it's just these halo exchanges are kind of the only thing. There's also no need to update these, the update steps, which means that as long as we build our model correctly, we put these halo swaps in, then the whole solver should just work. So that was fairly straightforward, I hesitate to say, but the more complex bit was actually the model building, whereby we now need each rank to build their own local grid. So this is some simple things such as point sources. That's fairly straightforward. There's other properties that require more distribution across the whole grid. But one advantage we had here was there's no existing OpenMP parallelization of this part of the code, which means by adding MPI here, there's quite a lot of room for improvement, because we're adding the only parallelization that we've currently got. The aim and what we managed to do was the result is insensitive to the domain decomposition. So obviously with the same input model, you can run it with different decompositions and the result should be ideally identical, like floating point precision. In most cases it will be. There's odd cases where just there's floating point errors, but it's basically the same. But in the building, most of the time you're just mapping from your global coordinate space to your local coordinate space. Fractal objects, the more complex geometry and IO objects were by far the biggest challenge, and that's mainly because they have more global concerns and global properties that needed to be added in. But hopefully the aim there was just to introduce those two steps to then look at the actual performance. So we started by looking at how this performed on a single node to kind of get an optimal MPI and OpenMP hybrid run to work out what the best configuration there was. So this was using a 1 meter cubed model, used as about 53 gigabytes of memory. And throughout these, the node is fully populated. So if you've got one MPI rank, 128 OpenMP threads, because it's work out how can we use the full node most optimally. And you'll notice in these between the building and the solver, they look quite different. So that for model building, we've got a pretty fairly linear increase up until 32 MPI ranks, and that's because all of the parallelization is from the MPI. It tails off after that, but that is because we're reaching the limits of the parallelization. The simulation there is running at a bit under 2 seconds to build the model, which was previously 90. So it's a bit over a 50 times speed improvement, but you're hitting the limit of what you can parallelize. That kind of 2 seconds of code is kind of still serial, every rank's doing it. So you start to see a limit of how much performance you can gain. And then in the solver, up until 8 MPI ranks, you're seeing performance increase and then it kind of flatlines. And you'd kind of, particularly in ARCHER2, you'd expect this in better performance as you go up towards 8, because once you're at 8, you've got 16 OpenMP threads per rank, which is the size of the non-uniform memory access in an ARCHER2 node. And so anything more than 16 OpenMP threads, you're reducing your performance there potentially. But then it stays pretty flat after that. But this is all a fully populated node, so there's not much of a trade-off there that we could see. But anyway, then we moved on to that was actually about a 3 times speed improvement based on the best OpenMP only run. So still nice to have. So then after that, we took the best single node configuration. So in this case, we took the 64 MPI ranks, 2 OpenMP threads per rank, and did some strong and weak scaling benchmarks. So the red line here is the weak scaling. So we're increasing the size of the model as we add more nodes. The blue line is our strong scaling, so one model and just throwing more resources at it. The largest model here was out of 64 nodes on the red line was, I think, 260 billion cells, about 14 terabytes of memory. So it's 64 meters cubed. Sorry, 6.4 meters cubed. Sorry. And you can see, again, the model building, the weak scaling, it's pretty linear. There's a bit of a drop off at the 64 node point. We're at about 63% parallel efficiency. In the weak scaling, it does drop off quite a bit after 8 nodes. that is, again, at this point, it's building in about 2 seconds. So it's it's pretty good performance. It just can't get any faster, really. The solver is arguably better. So the strong scaling, we're seeing it was at a 94% parallel efficiency up at 64 nodes. So still scaled really well. And that is a symptom of it's just this neighbor communication. So it does scale really well. And then the strong scaling, as you'd expect, a bit worse, but still at about 63% again, parallel efficiency. So still pretty good. You're still seeing performance by using more nodes. So the carrot for model building, this is all using simple geometry. So this is basically anything that isn't the stochastic, the fractal geometry. When you look at these, the performance characteristics vary a little bit more because the way these work inside the code is they are performing a fast Fourier transform over a 2D or 3D array of random numbers. So this is an array that spans the area that is your fractal geometry. And the first thing when you're doing fast Fourier transforms in parallel is it limits your domain decomposition. So you need to have a decomposition of 1 in at least 1 dimension. So at the bottom, we've got some examples here. So 1D slab decomposition or a 2D pencil decomposition. This doesn't have to be over the whole domain of the model, but it has to be over the whole area covered by your fractal geometry. You'll say your soil model or something. And the choice of your decomposition can also affect the performance. So for example, hopefully you see the pointer. If, say you had some soil model that took up half your model on this slab decomposition, if you had it kind of in this half here, you'd only have 4 ranks actually doing the processing there. And because the fractal geometry stuff takes more processing, you'll have your other 4 ranks which aren't processing it just waiting, and you've got a load balancing problem. But if you just rotate your decomposition such that it's covering, it's maybe this half of the model instead, you've got all 8 doing a little bit of it. And so you that's with the one occasions where how you decompose your domain does kind of matter a fair bit. But also because these are performing FFTs on random numbers, it needs to be reproducible in parallel, which is always fun with random numbers. But ultimately what you need to do is every rank needs to start from the same seed and reproduce all the random numbers in sequence, and then take the ones they want and discard the ones they don't. Just when we were looking at the kind of how this performed just in general, I found my initial attempt was around 100 times slower than the serial baseline, which was fun. Basically it was iterating over the whole grid, and it was at each point it was generating a random number and then deciding whether to keep it or discard it. And particularly when you do that in Python, you're using a very efficient NumPy random number call, pulling it hundreds of thousands or millions of times from Python, which is very slow. So instead, because this is a known kind of 3D domain, you can kind of calculate whole blocks of a whole chunk of numbers that you need to keep or discard, and generate them all at once with, again, an efficient NumPy call that then does it all at once and is significantly faster, as you can see here. So again, this is all single node runs. The MPI one, we ended up getting faster than the serial. There's not the same kind of, I guess in this case, 8 times speed improvement that we see with the simple geometry. And that is primarily because you're still having to generate all the random numbers of the rank, and the FFTs don't necessarily scale perfectly either. So it is not as good a performance improvement, but it is certainly, I'd say, faster in pretty much all cases, and certainly not slower. A few other things to mention is we updated a lot of the output file formats to support parallel I/O. So gprMax already used HDF5 for some of its output formats, but for visualization it used VTK, but it used XML file formats, which don't really work particularly well when you're trying to do things in parallel. So we used instead VTK HDF, which has a lot of the, well, has the advantages of HDF5 whilst directly supporting visualization. And this is because it's effectively a HDF5 file that has a defined internal structure, which is given VTK have a file, have a specification for. And the reason for choosing this is it means users can still run gprMax and then take a file that's directly and put it into something like ParaView. There's no conversion step. So we still wanted to be able to support that. It's worth noting the I/O performance is affected by the domain decomposition, and that's because you want your ranks to be writing out into the file contiguous blocks of memory, and so depending on your domain decomposition, you may or may not be doing that. VTK actually uses column major ordering, so Fortran ordering, so you want to decompose in your Z dimension. And currently it is only using independent I/O. It would probably get better performance with collective I/O, but for a couple of reasons we didn't get around to having a look at that. Then something else we thought was really important when we first started this work was correctness testing, particularly being confident that our MPI implementation was getting the same results as the serial implementation. So there were some existing tests in gprMax, and as Antonio said, they constantly are looking kind of how it's performing in terms of correctness, but a lot of this required manual inspection unless you were doing more analytical solutions. So we wanted to create kind of more automated test suites that could catch errors early and kind of just reduce some of that overhead and speed up our development. So these are all full model regression tests. They're not unit tests. But the nice thing about them is they let us directly compare results from non-MPI tests with MPI tests. So we could, have a non-MPI test with a known output and just run it with the MPI flag and check they're the same. And this is all put together with Reframe, which is a really great, it's written in Python. It's a testing harness designed for HPC. So it's effectively just lets you submit jobs to a system and then do whatever processing you want to do on the output. It's typically used for more system performance testing. So this is maybe a typical use of it, but we found really useful. And kind of you can put all this infrastructure in. That means kind of as it is now, it's fairly trivial to add a new test. You just need an input file, a few lines of code to kind of do the configuration and stuff. And then it will run and put it all into this regression framework, which was really, really useful for this project, and we were glad to do it, put it in nice and early. So then finally, I just want to show, because this was made by Sebastian, so a colleague of ours at EPCC, but it took the MPI version of gprMax and used it to visualize a kind of slightly large domain. This one's is through 750 million cells, I believe, so slightly smaller, but it does use fractal geometry and snapshots and stuff, which will increase memory. So this was run on 8 nodes of ARCHER2. Then the VTK HDF files processed by ParaView and with a visualization created in Blender. Just as a kind of brief, example. I think that is everything to cover. So it wasn't me and Antonio were both working on this. Craig Warren from Northumbria was also involved, James Richings from EPCC as well. But I think hopefully we've left a little bit of time for questions if people want to ask them. I can stop sharing this. Go back to the call.
Thank you very much, both. If anyone does have any questions, feel free to unmute and ask away, or if you prefer, you can use the chat function and type your questions there.
Should I answer that, Nathan, or not?
You can go ahead. I have opinions, but you're maybe better placed.
Thanks, Sebastian, and also very well done on the visualization. I like your brackets at the end, given funding. we applied recently to SSI for this sustainability fund for maintenance of open source or codes, and we were not successful. But I think if we are able to have some money, we would like to do the same thing pretty much with GPUs. We all know that there's a lot of GPU clusters that the main big supercomputers would be these days, and being able to do that with GPUs will allow us to do really a lot bigger things, even in smaller settings. So, for example, someone who has 3-4 GPU server, and it doesn't have to be Archer in a way, that will enable quite a lot of interesting work. There is a lot of things that we want to do. For example, being able a testing framework, as Nathan said, I mean, having that where the code becomes more complex and more different solvers and stuff, you want to be on top of them, and doing manually not very nice anymore, easy to break things up. Maybe also have more, I mean, we have a lot of documentation, but more documentation and better examples, and also to an extent, some documentation about you can go on and code things, because you know, as the code becomes more complicated, people who want to contribute, their pathway is not as straightforward to get into it. And for me, my pet idea for the next few years is to try to make gprMax more valuable and usable in other areas than radar, ground penetrating radar simulations. Which we want to go into these kind of other areas and make it more useful to other people in different research areas that use computational electrodynamics. I don't know, Nathan, you have more points?
Yeah, I mean, no, I agree. I think from a technical point of view, extending this to GPUs is kind of probably the next performance and capability thing. I agree with you on the kind of sustainability front. Like, so the regression testing framework we've put in currently, it works and it works great, but it's not portable currently. It doesn't need a lot of work, but it puts some time and funding to be able to do some maintenance to kind of, it doesn't handle floating point in precision, so it's kind of system specific, so the regression tests will fail outside of ARCHER2. So there's just little niggles like that which don't require a lot of effort and funding, but do require some. That are kind of important to do and thought, but yeah.
Okay, well, I would like to thank very much both Anton and Nathan. A fascinating project, and it's come on a long way. Long may that continue. Thank you both very much for your talk today. Thank you to everyone who attended, and we will have the recording of this available on the event page probably by tomorrow, in case you want to revisit any of it. Thank you very much, and
thank you, everybody. Thank you, Nathan, for all the hard work. Thanks, Claire.
Thank you.
Thank you. Bye.